add to the product experts, so just so that you know for your for the future, is that product experts works really well. It acts as an AND function. An AND function means that if any one of the experts is correct, then their product can properly model that. You can have also a sum of experts, like a mixture Gaussian model. However, then you would be taking an average. So if one of them is correct and then the other two are incorrect, then the average result will be average. Whereas ideally, at least with the product of experts, the correct expert would be, in the end, winning the, let's say, the computation. But in this lecture, we're not going to discuss about that much more about Boltzmann machines. So training any energy-based model follows the same pattern. So this is your definition. That's the definition for energy-based models. Again, we want to maximize log likelihood. So if we put this formula into our logarithms, then we end up with again an expectation of our nominator minus, because we've got an energy function here, like that's how we describe it, plus the logarithm of our partition function, of our normalization constant. And now this logarithm is a pretty nasty one. It has its log sum xp, right? So it's the logarithm of an integration over all possible inputs x of our exponential of our energy function. The denominator here is computing the expectation with respect to the data distribution we have, the empirical data distribution, what we observe. So basically our images in our training set. So we sample from it, sample from your mini batch, and then you can compute here the denominator. However, for the normalizing constant, you have to integrate over all of them. So it's not anymore the empirical data distribution. You have to have access to the distribution that we want to learn. So the normalization constant is independent of the empirical data distribution. It's not just we observe, it's like what we wish to learn. And that's because of the marginalization. The marginalization means we'll have to marginalize over all possible data, not just what we observe during training. So this is basically pretty standard, right? It's that's just a reminder. This slide as a reminder. Energy-based models, technically, again, we're optimizing them as usual. We have to take the log likelihood of our probabilities. Clear? What is difficult here? Where do you expect the difficulty to be? Exactly, right? Like if you've got here X is your data, like your image space, imagine you've got like millions and millions of pixels. It means you have to integrate over all possible pixel values of all possible pixel locations. That doesn't sound very easy and comfortable, right? And you have to do this for every evaluation. So for every gradient descent step. So focusing on a single data point, taking the logarithm of our log likelihood, like to see more, like to sort of spell out a bit more the difficulty. The logarithm of the log likelihood, its gradients is, we have to take that's the denominator, minus, because it's an energy function, minus the gradient of the logarithm of the normalization constant, the logarithm here we're using, like in the reinforced trick, we're using the fact that the logarithm of a function has a gradient which is 1 over fx times the gradient of the function itself. That's a simple identity property. So here from the logarithm, we go to the derivative of the function itself, the normalization constant with respect to the parameters, scaled by the 1 minus the normalization constant. The denominator remains always the same here, like only the denominator changes, and we're manipulating a bit the computations. And now from here to here, from this step to this step, we simply replace the normalization constant with its actual formula. So it's the normal and marginalization over all inputs x prime of the exponential of the minus energy, and then the derivative of that energy function. Is this clear? It's yeah, you have to see it step by step in the slides, but the idea is the idea clear? Like, no, let me rephrase. Is there something that looks particularly weird? I understand that, you know, when I just show it here like that, I show it on a purpose like that because I just want to show that it's not like even magic or even that hard. That's why I have to put like all the math simultaneously. For me, it's more important to let me know if the basic steps, is there something that looks weird or unclear? We simply take the derivative of the log likelihood, which means then, because it's a ratio, the logarithm is numerator minus denominator. The denominator is just the energy function, doesn't change. So it's basically our backprop gradient for our neural network. The denominator is the normalization constant after computing the logarithm. The logarithm can be easily rewritten with the identity for how to compute the derivatives of the logarithms. And then the function f of x, we replace it with the definition of it, which is the exponential of minus energy over its marginal. It's marginalized version. Like, that's it. And then if you write this a bit more succinctly, this is the gradient of the logarithm of the gradient of the log likelihood is equal to the gradient of your energy function. So basically your neural network definition, your backprop gradient, plus the expected value of our energy function on randomly sampled points from our data distribution. But the learned one. Here, before we were using the empirical data distribution, like for x, so x is any random point from our training data. So, I don't know, I don't want to see far, MNIST. I randomly sample one digit, that's our x. And that's very easy to compute, right? Like I pass my MNIST digit, my MNIST 6 through the neural network. Even with random parameters, I mean, the parameters might be random and not correct yet, but it's easy to do the forward computation and then the backward computation. That's the gradient, the denominator. And the denominator here is very similar in form. It's still the gradient of the energy function. However, now instead of taking one of my MNIST digits from our training set, I have to sample new digits from my distribution that I'm learning at the moment, p theta. And this is p theta because this term, this exponential of minus energy over the zeta theta here is literally that, is p of theta of x. So intuitively, this means that, why do I take gradients in the first place? Because I want to maximize my log likelihood, right? Like my model in the beginning is random. I want to take gradients in the direction such that my model becomes better. So my log likelihood for the observed training data is high. So I want to, like when I want to increase that, when I take a gradient to increase that, means I want to take a step towards reducing my energy or increasing my nominator, like that corresponds to the nominator. So I want to pull up my nominator in the observed training points. This is the correct answer here. So it's like my digit from my MNIST. While at the same time, I want to push in the opposite direction. So you can see here, minus and plus. So here I want to pull up, while here I want to push down the denominator. I want to push down the energy in all other locations around my observed points. How do I know what are the all other locations? Well, normally we would have to go over all of them, because the expectation here is literally a marginalization. Alternatively, I can try to sample from it. So I cannot really marginalize the whole space often or usually. However, I can try to basically sample from my current model that I'm training and say that, you know, my sample should have lower likelihood, like compared to my observed ones. Is this clear? So you can see this again in the ratio of likelihoods here. We want to maximize my likelihood on my observed points while minimizing my likelihoods or my energies on all other points that would be randomly sampled otherwise. Okay? So beyond generation, we can use this for anomaly detection. If I have a point that looks very weird, I can use the ratio of likelihoods to say, okay, this point is much less likely to happen than my observed points. We can use it for denoising or restoration by finding pixels that are more likely to occur than not, or for classification. So energy-based models can also be used so that if I simultaneously add the picture and the label, the energy for the combination should be lower if this combination is correct. Any questions on energy-based models overall? Like this is like really the basic, it will be always the same. It doesn't change. No matter whether you have Boltzmann machines, product of experts, score-based models, and what have you. Is there a slide or something like that looked awkward? You can be forthcoming here, so don't worry. It's, no. Okay, we'll see. So Boltzmann machines basically are inspired from physics applications, and again, we start from an energy-based model definition. The question is, now we want to model. We want to define a model. So how are we going to define an energy function? Well, the Boltzmann machine says that the energy function is simply this quadratic function of the input with itself. The parameters of my model is how I combine the inputs, so how I combine my pixel dimensions. And I have also a prior term, which tells me how likely each of the dimension is. Now, if X is my image with 65,000 dimensions, grayscale image, our parameter matrix W, so here theta corresponds to W and V, right? Just to clarify, theta here then this means that my parameter matrix W would have to have 4 billion parameters, right? Because it would have to have the shape. So that's my, that has the shape of x and shape of x. So 65k, 65k. So the number of parameters here is 65k times 65k, more than 4 billion parameters. And that will be per layer. So if I would have even like deeper networks, that would not be very easy to handle. Because we have an energy-based model, how do you sample from an energy-based model? You can't really have a prescribed way of, like with Gaussians. You're just given an indirect way of computing your distribution, and you will need indirect ways of sample. So if we have P of theta, so my input, then I can then use MCMC or Gibbs sampling to sample. Now, because Boltzmann machines, the normal Boltzmann machines are too expensive to handle, restricted Boltzmann machines were proposed. And we can simply reduce the complexity of a Boltzmann machine by introducing a bottleneck feature, Z. So now our quadratic term does not go from my image space to my image space, but from my image space to a latent space, and then the latent space is much smaller. So which means that my parameter W will be also, my parameter matrix will also be much smaller. The quadratic term captures correlations. So it says how different pixels and latent variables correspond to. So you can think of this as features. And the unary terms capture priors. So how likely particular pixel values or particular features are. So RBMs are a practical solution to the real problem of having too high dimensionalities with images. Unfortunately, introducing latents brings one more complication, because now our latents are literally unknown. We don't know them, so I have to integrate them out. So in our, not only now we have an integration in the denominator, but we have now one more in the numerator. So why is that even a good idea? Well, if you have 4 billion parameters in the first place, that's a no-go anyways. So we just have to find ways of computing the denominator here easily. Now, because this is actually not anymore an energy-based definition, technically we can rewrite it so that it looks like energy-based by introducing the concept of free energy, which means that basically you're saying that this sum of exponential of minus the energy is equal to the exponential of some energy function, free energy function we call it, and then we just rewrite this. Like the exponential of the minus free energy is equal to the sum of the exponential of the minus energies. Then we take the logarithms here, and that's the free energy. So this is just again a way to rewrite it. We don't really need it in practice, unless you really want to compute somehow the free energy or you want to do something with it. I'm just mentioning it here in case you see it ever. The basic reason here why we have or why we want the free energy is because this is not an energy-based model anymore, at least in the way that we stand conventionally. For an energy-based model, you need an exponential of an energy function, like that's the standard definition, whereas here you've got the sum of an exponential of the function. Okay? Now, because we have x and z's here in a single formula, there is no direct flow. So RBMs are actually not feed-forward models. they are defined jointly. Like, to obtain z here, you don't need to know x per se. The latents z are depending on x here, but x also depends on z. There's forward and backward flow of information. This is not cascaded computation, right? Like the energy is a function for which there is no arrow of time. And that creates a problem because things are much simpler when you've got forward computations, when you've got feed-forward computations.
A question.
Yes?
I still don't quite get what's the idea behind free energy, or why do we need that?
In practice, we don't need it,
Yeah.
like to implement a model. However, if you want to do some analysis of it, the free energy might be needed for mathematical, let's say, derivations. In practice, like in theoretical derivations. In practice, like it doesn't really change. Of course, you might want that also in practice if you want to have easier computation. So because then you've got logarithm of exponential, and then the logarithms and the exponentials cancel out, right? Whereas here, if you put the logarithm here in the denominator, you won't cancel, like the two won't cancel out. But of course, that depends on what kind of library you use. If you've got, so for instance, with PyTorch, there are efficient implementation for log sum XP and so forth. So it really depends in the end also what you have in your availability for your program. Now, is this clear? So for a neural networks normally are feed-forward models, correct? So if you go, this is a bit sensitive to explain. Let's say I have a neural network. This is X, correct? So, okay, neural network is not necessarily probabilistic, but that's not the point here. The point is to explain why this is not a feed-forward architecture. So when you go to the neural network, that's your X, right? So when you go to your output here, it's going to be, let's say, Z. So Z depends on X and X only, correct? To compute the Z, to compute your features, you only care about what your input is. And of course, what's your neural network, the weights and the architecture, correct? So this is feed-forward flow. Z is equal to f of x. In an energy-based definition, you don't have that. It's not Z is equal of f of x, right? Instead, we're having a more general function E, like our energy, which couples the two together, but there is no explicit definition for going from X to Z. And what is the problem here? The problem is then that for Z, we don't really know, we don't have values, right? Like we're computing, like the values of Z depend on parameters W. X, we have, it's the observed values. However, the latent variables Z are not observed. Which means that our energy function changes, our variables Z change with the training. We cannot use easy feed-forward propagations only. Now for RBM specifically, we also have to define how we compute the probabilities. There were two assumptions, practical assumptions at the time. We consider the pixels, the observed pixels, to be independent given the latents, Z. and each of them is a sigmoid. And also the other way around. So our latents are independent with respect to x's, and our x's are independent, like in terms of dimension per dimension, with respect to latents. We just consider them like independent. And since x depends on z and z on x, because we have no feed forward, so z influences x and x influences z, it means that we cannot really have just one feed forward computation. We have to do it in an alternating way. So from z via the probabilistic model, because we have to sample new data points x, right? Like in our training. We have to, this is easy to compute. That's just the energy function computed on our training points. But we have to sample now new points from our distribution that we're learning as we go. So how do we sample from here? Well, if we had the feed-forward model, it would be simpler. However, we don't have a feed-forward model. So what we have to do instead is say that, okay, we start from some good guess for z, then via our probabilistic model defined here. I forgot to add the z given x, but it's the same actually, but reversed. So from z, we sample a possible x, and then given my better guess of x, I sample a better guess of z for z, and then a better guess for x, and then I get a better guess for z. And that's a way that I can sample now from my learned distribution. Now for the, this is a bit more complex, but I add this slide because it's not obvious like to find it online. However, the basic idea, I'm not going to go through it step by step in the interest of time, but the basic idea is similar to the previous slide without the latent variables. So here again, it's the numerator and the denominator. The denominator has the log of the energy function, and we're taking the derivative of the logarithm like identity. Here is exactly the same. Exactly the same. We only need to add one more summation because we have to sum over the latents, and that's it. The form is basically very similar in the end. I added all the steps for your convenience so that you can see that later on your own. But basically, again, we have to evaluate the energy on the observed points x. So these are our MNS digits, let's say. But now because we have a latent, we have to sample from our latent distribution using the alternating scheme that I mentioned before. Plus, now you have to sample both from your training, your observed variables x and your latent variable z. The only thing compared to different compared to your to the previous energy-based gradients is that we have the latent variable that we have to integrate out. Otherwise, the formula is exactly the same, and the steps are nearly identical. The first one is easy to evaluate. Before is also easy to evaluate. You just pass your MNS digits through your neural network. That's your energy-based function, and you compute the energy, and then you backpropagate the gradients. Now you have to integrate over our latent variable z. So you have to account for all possible z's. However, the second term is harder because we need to sample now. We have to sample from both x and z jointly. And we sample using MCMC or Gibbs. Gibbs sampling is a better way of doing MCMC per dimension, or it's a faster way. It's guaranteed to converge over many rounds. However, the problem with MCMC and Gibbs is that it is guaranteed to converge, but only in infinite steps. So basically, here, we are guaranteed to sample from the correct X and Z, which is then required to compute this one. And this is needed so that we can maximize the logarithm, the log likelihood. So it's it's a bit complex overall. But only if we have infinite time, so infinite steps. And this for one gradient update. So we have to take infinite time steps of one gradient for one data point. Clearly that doesn't really work, right? Like that's obviously intractable. Not only theoretically, but also computationally. This is why contrastive divergence was proposed. Now, contrastive divergence is a bit of an older algorithm. However, you will see it every now and then. And its basic principle appears also when you're optimizing energy-based models. Let me re-emphasize, because even if you don't remember all the math, it's like a bit hard also to keep in mind after a bit. The basic principles remain. So it's really like nothing really magic, just taking derivatives of functions like nothing else, and a logical approximations were needed, reasonable approximations were needed. However, the intuition is very simple in the end. The gradients, what the gradients are supposed to do is that they pull up my nominator on my observed points while pushing down my denominator on all other points. If anything, you should remember this. Energy-based models, with energy-based models, you want to compute gradients because in the beginning they're random, right? You have to have a way to improve them. You have to have a way how to make the model compute higher likelihoods on the observed training points. However, if it's just about the observed training points, then you would just overfit there. You would ignore the rest of the training space because, again, the function f in the denominator is infinitely flexible in principle, right? Like you have a very flexible function. The denominator regularizes. So it says, I want to make sure now also that my energy, like I still have energy also in all other parts of the space that are next to my observed points, however, a bit lower. Now, the problem with the maximum likelihood is that we have to take infinite steps. So what Geoffrey Hinton, you know Hinton, right? What he proposed back in 2000 something was contrastive divergence. Contrastive divergence is another learning objective, not maximum likelihood, it's another objective. It basically replaces the maximum likelihood. Why the maximum likelihood? Because the maximum likelihood requires infinite steps to compute the gradients, to compute gradients correctly or accurately enough. So what is the intuition between contrastive divergence? Well, Hinton said that maximizing the likelihood is very similar to minimizing the KL divergence. The KL divergence is a metric, is a measure for between distributions. So it's like saying if I maximize my likelihood, it will be similar to if I minimize my KL divergence between two distributions, the true data distribution and then one that I am learning right now. If I take now this KL, assuming that this is correct, was his intuition, right? Like assuming that this intuition is correct, what does the KL look like? Well, the KL is the P of the data times the logarithm of the data, the probability of the data over the probability of the model. We take the logarithm, like the logarithm of a fraction is the difference in the end. Now this first term cancels out because it only depends on your data. It's not on your model. So when you optimize your KL, this does not change. It doesn't have any theta in it. This is the only term that changes. This has theta. And Hinton said, okay, after MCMC steps, we cannot avoid the MCMC steps. We just want to make them easier to compute. We just want to get there faster, not with infinite steps. He says that when I have this KL that I want to minimize, this means that the model that the optimal model in infinity is the correct one, which should be the closest to our true data distribution. Well, I want after n steps my model to, so basically I want my model to learn as quickly as possible. After just n steps or just one step, I want my model to be already as good as if I were to sample infinity. Basically, I want to, with one step, I want to be really, really close to my optimal model. So that's the intuition with contrastive divergence. Like that's a bit, okay. That's the contrastive learning objective. Is this, like, let's discuss it. This is the optimal. P theta, this is the optimal. So maybe I should have put here the infinite. So in the optimal, in the limit, the best model that I can have, it might not be perfect, but the best model that I can have will minimize this term, the KL divergence between my data distribution and whatever my model computes. Like that's the best possible. I cannot do something better than that. That's in infinity. Now here, Hinton said, okay, a learning objective. So what is a learning objective? A learning objective is an objective that will bring me to good enough parameters as, best as possible. My learning objective is, okay, I'm not going to care anymore about my data, which require infinite steps. I just want to ask my model to get at the best possible it could do anyways, faster. Not with infinite steps, with one step, or two steps, or n steps. Like that's it. That's the contrastive divergence. There was a hand before?
No, it was answered.
Okay. Contrastive divergence has the following advantage. It removes the requirement to sample from the convergence model at infinity. I don't have to have infinite steps to get there. By optimizing contrastive divergence, by saying that I want my model to be as close as possible to the optimal one after just one or two or n steps, means that by the definition of this, like I optimize for that, it means that my model does not require infinite steps to get to optimality. Of course, the question is, you might want that. It doesn't mean that the model will do it. But this is the objective that you're literally optimizing. So we want to make sure that after n, often one is enough, sampling steps, the model is not far from the data distribution. At least that's the objective. Again, whether the objective is well minimized, or if it's easy, or if it works in practice and scales up, that's a completely different question. But that's the objective that we're optimizing, and for particular data setting, this works. This looks like minimizing a reconstruction error. So if that's my observation, I sample for one step. So h here is z in my own equation. That's from a figure from their paper. I sample a latent. You sample a latent by a Gibbs sampling, and then you sample again observed variables, conditioning on the latents. And you want your observations and your sampled observations to be as close as possible. So basically this looks like a lot like a reconstruction objective. That's an intuition, like that's one intuition on why contrastive divergence can work or could work. That it resembles a reconstruction objective. And because in our probabilistic model we assumed that our dimensions for our latents and our dimensions for our observed variables are independent of one another, conditioning on either the latent or the observed, depending on the flow. It means that we can compute these things in parallel. We don't have to have sequential computations anymore. We don't have the chain rule of Bayes for our computation. We just compute everything in one pass. So, as a pseudo algorithm, we sample a data point X, we compute the posterior, we sample the latents given the posterior, then we compute the conditional, we sample an observed variable, and you want to make sure that it is as close as possible. This is a contrastive divergence objective that replaces the maximum likelihood objective. So the same way we were computing the maximum likelihood gradients, now we have to compute contrastive divergence gradients. If we do that, then basically this looks similar to maximum likelihood gradients. Again, we have to compute the derivative of the gradient of the energy function for our empirical distribution data, plus sample data points. There are some extra terms, but they cancel out because they are small enough, or at least that's the assumption. We just ignore them. So there is a bit of bias, but in practice, at least in the original paper, it worked. And again, one more time, the intuition behind any of this, behind anything, whatever, like if you want to train an energy-based model, there are two, like there's one important thing you want to optimize. You want to make sure that your likelihood is high on your training points, but that's not enough. If you just ask that, like in the case of normalizing flows, you have very high peaks of probabilities only on your 10,000 training set samples, because this is the only thing that the model observes. That's not good enough. It means that if you move like one coordinate to the left or to the right, the probability will go suddenly very low, which means that the model doesn't generalize. So you want to make sure that your energy does not pick out. So if that's your x, and then that's your p of x for your energy-based model. If, let's say, you've got these data points, you want to make sure you don't want to get this type of distribution, right? This is what the model will do if you ignore the denominator. The best way you can maximize the likelihood, the log likelihood, for your training data is by putting infinite probabilities on the observed data points. However, this is not logical. What you want instead is have something more smoother. You want to have something like that. Right? It's a bias, inductive bias. It cannot be that nearby data points in the pixel space are so different. They have to be similar. So the probability has to be similar. And this is what the energy what the denominator does. Like you want to make sure that now in the 2D space, you need to have enough probability also around your training points. However, these probabilities should comparatively be lower than your true observations, right? Because your true observations are things that you've observed. So the closer you are to things that you've observed, you would like to have more likelihood, but for everything else, you'd have to have lower likelihood. And this is what the denominator says here. The denominator should push should assign enough energy on locations in the space that are close enough to your observed points, and very low energy, very high energies on points that are too far away, but not zero in principle. Or at least it should not be that you only have very picked distributions. Is this clear? When sampling with restricted Boltzmann machines, we can sample with MCMC. So we initialize X randomly. You add some noise to your data point. If the energy, if your nominator gives a better value, then you keep it and continue. If not, we sample with that probability. So basically that's like exploration versus exploitation. If our new, in our new time step in our sample, in our MCMC chain, we have a better sample, then we keep it, we exploit it. If not, we don't discard it because we want to explore. So we keep it with a probability that is proportional to how to our likelihood ratio. Again, because it's a likelihood ratio, we don't need a normalizing constant. So that's good for us. We don't have to compute ugly integrals. However, the computation is sequential, so we have to take an MCMC chain. Why do we need an MCMC in the first place? Because we don't have a canonical probability distribution. Our distribution is literally a neural network, right? Our energy-based model is a neural network, and the neural network defines the denominator, like that's our energy function. And we need easy ways to manipulate that to be able to train it. Not easy ways, smart ways to be able to train it. But once we have converged, we don't have anymore anything that looks like a canonical distribution function. Or have a neural network. How do you sample from a neural network? Well, when you've got like that type of models, you can use MCMC to sample. Another MCMC approach, yes?
Maybe on the last slide. I think I missed something, but maybe I missed something, but we're still in this strict Boltzmann machine setting. But here our energy-based function is suddenly no longer with H or the Z or however you want to call it.
Right. So
we have to do this simultaneously, right? This process of like sampling to.
yes. So yeah. Okay. Yes. Correct. So in that case, we have to.
Okay.
So this is again the general case. Yes. And for RBM sampling, so for sampling, we can also use MCMC with Langevin. So which is well, basic, simple. It uses the score function, and that's what we're going to see next time. So with score function, you can also compute very easily. Well, not very easily, but it's another way of computing samples from arbitrary distributions that you've already learned. By basically, you don't have anymore the acceptance criterion. The good thing about Langevin is that because you don't have this acceptance criterion, then the if then else here. So the problem here is that you might have a lot of samples that are being rejected, like that you have to repeat a lot of computations because of this if then else. Whereas with Langevin sampling, you just do this continuously. And well, I'm going to discuss this a bit more detail next time. So in the interest of time, I'm not going to go deeper here. What is, however, important to note here, this is the score function, which is the gradient of the logarithm of the likelihood. Like with with MCMC sampling, you also don't have normalizing constant here, right? That's very important, how we avoid the normalizing constant. Well, with RBMs, you get good enough generations at the time. Deep belief networks are basically stacked RBMs. So instead of having just 2 layers, you could have more. train them per layer. So you train first layer, after convergence, then you train another layer, and so forth. So it's not end-to-end training. And because of this, these are directed models, right? Because so between x and z, it's not directed anymore. You know, we stuck them. And also the same from z1 to z2. But overall, it's a directed model because you first have to compute z1, and then you have to compute z2 given z1. They're not easy to optimize in general. Like and these models are the early deep generative models, so it's good to have them because you might need them in the future again. Yeah, deep Boltzmann machines was like another variant where basically we combine Boltzmann machines, restricted Boltzmann machines. Sorry, you're taking here the RBM layers from above and below, so you create the Markov blanket. Then the energy function here is, well, it goes all over the place. You got from x to z1, from z1 to z2, from z2 and z3. And as you can imagine, that creates all sorts of intractabilities and complications. So, well, there are complex, very complex training methodologies here, even more complex than contrastive divergence. Like you have to start using variational methods or other sampling methods. Generally, these models don't work that great in practice. Nowadays, they are massively replaced by whatever else we have discussed. Oh, sorry. And yeah.